Okay, so hi everyone, Senan this side, and in this video we are going to solve this linked list in a binary tree. So what you are given is a binary tree, and the root would be given to you, and a linked list with the head as the first node. You have to return true if all the elements in the linked list starting from the head correspond to some downward path connected in the binary tree, otherwise return false. So basically what you have to do is you'd be given a linked list like 4 to 8, and you need to find a continuous chain of nodes in the linked list or the tree where you can match the elements of the linked list. So linked list is 4 to 8, so 4 to 8 is present in this tree. Similarly, in this case 1426 is a linked list, so 1426 is present, so you return true. Right now if you observe, the answer need not start from the root, need not end at a leaf in the tree. So linked list should be a part of the tree, may or may not be the root or the leaf node in the tree. Could be either of the case. Okay, so question is quite straightforward and it's obvious, not not exactly obvious, but the idea that I would be using is for every node I'll try to correspondingly match the linked list with these elements, right? So I'll assume this is the start, and I'll try to search 4 in this node. So 4 won't be there, so I'll go to the left and go to the right. So first, while going to the left, I'll see is 4 there? Yes. Then can I find 2? Yes, I can find 2. And then after that, can I find an 8? And that for that answer is no. Okay, so left side there's no linked list. On the right, yes, I can find a 4. Then I can find a 2. Yes. On the left hand side there is no 8, but on the right we have an 8. So 4 to 8 exists, and then what? Then we return true. So first of all, this is the function. So just understand the base cases because I'm writing a recursive solution. So if head is null, so head is what? Head is the linked list. So I'm saying if head is null, that means there are no more nodes in the linked list. If that is true, what I'll say is return true. Since there are no nodes in the list, so in a way that linked list is present in the binary tree, right? Otherwise, if root is null, so if head is equal to null, we return true. But if head is not null but root is null, so that means this if statement. So if head is not null but root is null, so that means I'm not able to find the linked list starting from this root, because the root is null, so there are no more nodes to check exactly. Okay, so that is why root is null, and that there is, and for the same reason I return false. Now what I do is I try to match the list. So given this head and the root, I try to match is this 4, and if yes, then its children are 2 or not. If yes, then is its children 8 or not, something like that. So you're trying to match the linked list with the binary tree, assuming the head is the first node in the linked list, or head has the value, or the root has the value of the head of the linked list, assuming that. Otherwise this would return false. And if I'm not able to find the linked list starting from this root, including this root, what I'll do is I'll try to search the left side of the tree and then search the right side of the tree as well, right? Because this is a binary tree, so left or right. Suppose this was n array tree, so you'll just write a for loop for n iterations. Anyways, now let's look at this match list. Again, match list has the same logic as here, right? So if head is null, you return true because you found a linked list in the tree. If root is null, you return false because head is not null. So that means in this case there is still an element left to be checked in the tree, but the tree is no more. In a way, that's a null node. Otherwise, what I'll say is if head's value is equal to root's value, that means this could be a possible start. So what I'll do, I'll try to match the remaining list, that means heads next, and on the left side of the tree. Similarly, if that is false, I'll try to search the right side of the tree. Fine. And otherwise, if head's value is not root's value, that means we cannot match the lists. In that case, I return false. So yep, that was the whole solution. It's quite straightforward, nothing much to do. The code is also clean and simple. And this is the brute force approach, and the time complexity is n times m, assuming n is the number of nodes in the tree and m is the number of elements in the linked list, or the other way around. You can just interchange n and m, it's no issue. And the space complexity is what? Space complexity would be the height of the tree plus the height of the tree, or the what do I say, the height of the tree and the length of the linked list, right? So the minimum of that could be the maximum case, because if length of linked list, or not exact, So this would be the max of the height of the tree and the elements of the linked list, max of that. Because let's say you are checking this head is of size, let's say m, but is subpath, you'll go to the leaf node, and even after that you'll try to check head is present or not. So yep, you cannot find a linked list which is having more nodes than the height of the tree itself. So yep, that was the whole video. It's the brute force approach. I've seen more variations for, like, when you see search solutions, you'll see for a KMP solution. I'm not going with that. This is the brute force. This is the most clear explanation, the clear solution, and this works. If it works, don't touch it, right? Whenever you do some sort of development, if it meets the constraints, don't try to optimize that, because there's a cost associated with optimizing the stuff. So if it matches your constraints, don't touch it. So yeah, that was the whole video, and I'll see you in the next one.